for example, the camera. But the camera is not enough, because in certain conditions, when I'm coming out of a tunnel into the bright sunlight, the camera is blinded. So what I'm doing, I'm adding an additional radar sensor system or a LiDAR sensor system. With all of that, I can already be better than the eyes of a human being. But what I also can do is I can add here car-to-car communication, which is basically bringing information outside of the line of sight. Over 1 mile of distance, I can be informed that there is an accident. And within 5 milliseconds, I know that there is something happening in my environment, that the traffic light is going to go to red, that there is an ambulance coming from the right side, and so on. With all of that, for the first time, a self-driving robot gets better than a human being, because a human being can only react to what you see or hear, so line of sight or line of hearing. Here the machine gets better. And the good news is, for NXT, that basically what you need is all that technology for sensing, thinking, and acting. So every robot is sensing its environment, is taking the driving advice, and is sending a command to the arms and legs. The orange boxes here mean this is the portfolio where NXT is either a market leader or has a very, very strong portfolio for the emerging markets. And you see it already. We are probably the only company in the automotive industry at the moment that has from A to Z all silicon that you need for building such a robot. And this is why I said in the beginning, this is exciting me so much that I have all Lego blocks in my own little toy shop, and we can play with these innovations. Everything in all one little chip that is smaller than my thumbnail. So really highly up-integrated compared to the big radios from 5 to 10 years ago. Of course, quite a step up, also power consumption reduction, form factor reduction, and the performance upgrades. We are leading in the car access domain, so this is the convenience part. But most important for the discussion today will be here this ADAS, Advanced Driver Assistance System part, where you can see how the robots will behave in future. Okay, a lot of this technology that I have just addressed is available for consumer electronics already since years. So how can you make money out of that in the automotive domain? Well, the simple answer is just the functionality of a chip is not enough. As I had said, the automotive industry is trying to get the human errors out of the ecosystem, but there is, of this tetrahedron as I have called it, there is 3 other axes that we need to optimize. And what we need to optimize, and this is well known, we do this since 30 years in the automotive industry, the component reliability, to making sure that the components, the chips are as robust as possible. This is what we try to do with our ACQ 100 qualifications robustness tests. This is nothing new, pretty boring stuff. What is coming in here now are 2 new trends. And the 2 new trends are functional safety, and the second one I have called functional security. So functional safety means that a car maker has to look at the entire car and has to say, under all circumstances, this car must not create a fatality, so must not kill or injure people. How do I do that? Well, I look at each single function of the car, and then I evaluate how critical is it if that function fails. Okay, power steering. Electrical power steering, what happens if that function fails? Well, the clear answer is it depends. It depends whether this is a power steering in a little Fiat 500 car, then probably nothing happens. It's just less convenient to steer, but you can still drive the car very normally. If the same function fails in an F350 Ford truck, and you have a 45-kilo lady behind the steering wheel, well, the answer might be that it can create fatal accidents because that lady cannot steer that truck anymore. So, in that ecosystem, you see, we need to go from the system level, we need to evaluate each component, and then we need to say, where do we need redundancy, how do we build up our systems, and how do we optimize the functional safety robustness, and very newly, that same system assessments you have to do for car hacking. What we see, and what we have seen over the last 2 years, is quite massively hackers now intruding the car, hacking into the telematics system. One of the very famous was the Jeep hack last year, two NSA hackers hacked into the Jeep, and then via the telematic system went into the engine management compartment, stopped the motor of a test car on the highway, switched on the infotainment system to maximum volume and the window wipers, which is of course pretty nasty functionality if that all happens to you while you're driving on an occupied motorway. Yeah. So we need to make the cars robust against all those areas, and this is of course, in other words, value creation for us as an innovator industry. Why is that all so important? Well, it's dollars. Last year was not only the year of an all-time high of car sales that we celebrate, but it was especially also the year of an all-time high of car recalls. And you know some of the very famous topics, airbag recalls, key malfunction and the like. This was billion-dollar recalls and the ruin of some of the big innovative tech companies on the globe. So by all means, you have to master that, because otherwise this can really ruin big car makers and you as a supplier as well. So with all of that context, I'm going to give you a few of the examples of the hot innovations that we have at the moment in the kitchen and that we are driving into the market big time at the moment. And the first one is 77 gigahertz radar. So as I said prior, for a self-driving robot, you're going to get more and more radar systems that are watching what's going on around the car. Such a radar system has a range from 0 to 120 meters for a short-range radar, up to 300 meters for a long-range radar. And at the moment what we have is we have long-range radar systems, typically in adaptive cruise control systems for cruise control management. In future you will see really these radar cocoons showing up completely around the cars. And what we have tried to do at NXP is we have tried to optimize these 80 gigahertz send and receive chips. So if you can do this, if you can produce them in CMOS, plain vanilla CMOS technology, then basically you're in the same technology like the microcontrollers that we have in use. If you have those components all in the same technology, yeah, then the semiconductor industry again of course has the advantage, we can up-integrate. We can suddenly start making out of multi-chip systems a one-chip system. We can save a lot of power for these systems, we can shrink the overall systems with very tiny radar systems and can make them very, very robust, easy to use for the tier ones and for the automotive industry. So in other words, what we want to build is single one-chip radar modules that are very, very efficient and can be placed all around the car. We are playing with our radar modules with a company in California, Google, already since 2 years, and they are using these modules very actively and very successfully. And these little rolling phone booths that Google has on the road, they are, for example, operated with our radar systems. What we also can do is we can take more of those radar front-end sender and receiver chips next to each other, and we can build very, very powerful, very, very high resolution radar systems. So these high resolution radar systems basically are 12, send, 16 receive channels, and you can sweep the beam through all the place, and you have a very, very good illumination, so to say, of your obstacles in front of you. You can very, very well detect what is in front of your car. And this is basically the electronics that we have in use at the moment. So just to show you the comparison, this is the little radar stand that I have there on the picture. So this is, we call it really stand because it's the size of a postage stamp, 3 by 3 centimeters. And what you see here on this thing is basically how NXP and Freescale came together as one company. It's a very nice example. We have this, we have this tiny CMOS chip here that I was talking about from former NXP. Then we have the radar microcontroller from former Freescale. And if you turn that module around and look at the back side of this module, what you see is, oh, there are the power management ICs for this whole circuitry from Freescale on the back side of that module. And from old NXP, we have the CAN and Ethernet physical layers also on that module. So in other words, this is really a very nice showcase how to see how all these Lego blocks from two companies come together and we have a complete solution to offer that is tiny enough to replace ultrasonic beepers in the car, build a complete radar cocoon, and you can do everything from 5 centimeters away from the car parking use cases, so really for these near-field self-parking use cases, but you also have while driving blind spot detection, lane departure warnings, forward collision warnings, and all the like with the same type of radar electronics. Very hot innovation at the moment, and we are working with most of the big car makers at the moment worldwide to design that in. The other thing that is coming is car-to-car communication. And car-to-car communication is in the press since quite some years. We had a lot of activities, field trials in Germany, so my home country. We had a lot of activities in the US. And then I got personally surprised when Reger, our country manager here for Korea, he just told me, yeah, Lars, now we're going to overtake you. We are faster than you. We are faster innovating. Because for the Winter Olympics here in Korea, we're going to install a test track 90 kilometers from Seoul to the Olympic area, and we're going to deploy here together with ISIS, a Korean company. We deploy car ITS systems able to be LMP based, and basically we have roadside infrastructure where traffic lights, road signs, the traffic management infrastructure can talk to cars and buses, can in real time deploy the information into the vehicles. And this is, of course, the use case is, you know exactly hundreds of meters before you reach a traffic light, when this traffic light is going to switch to red, you know where a traffic jam is, you know where ambulances or police cars are driving to clear the road. So you get just much better context information about your environment. And of course, with the smoother traffic flow, you can avoid even accidents up front. What are the main use cases, of course, that are of interest? Well, for example, the motorcycle approach is a very nice case. So you are driving behind the truck, you want to overtake the truck, and the motorcycle is coming from the front. You know before you get out behind the truck that there is a motorcycle coming. When driving over crossroads, you know if there is an ambulance driving into the crossroads. When you are an ambulance, you can switch over 1 mile of distance. The traffic light to green already for you. So there is no ambulance driving over a red traffic light just because the traffic light is too stupid to realize that there is an ambulance coming. Yeah? So for all of these service vehicles, that is of course a big advantage. And the most sexy use case that I know at the moment is this truck platooning. And truck platooning is basically what you will see on the next video. I think you need to go to presentation mode, otherwise you cannot start it. Okay, so what you will see there is basically truck platooning means one truck is in front and all other trucks are following, like on a virtual tow bar. So basically the drivers are hands-free and they are just following, like a trailer, the first truck. If you just click on that arrow. There you see what's happening. Do not see what's happening. Okay, I think it does not work. But no issue. So I'll explain to you what you should have seen. So basically what you're seeing is a... Just go to the next slide. I can explain there what this thing is doing. So what you have basically is you have radar systems and you have car-to-car systems in each of the trucks. And you see here there have been 6 trucks in Europe on the roads. 4 of those 6 truck companies were using NXP silicon, so the car-to-car silicon, and they were also using the NXP radar systems. And what then happens is the following. These trucks are driving at 80 kilometers an hour on the road, and they are driving at 11 meters of distance. So they are following each other very, very closely. And if the first truck is doing an emergency braking, so is hitting the brakes, within 0.3 to 0.5 seconds, the second, the third, the fourth, and the fifth truck, they know it immediately. The signal transmission is in the range of 4 milliseconds. So the first one is pulling the brake, and All other trucks following know 4 milliseconds later that there is an emergency braking of the first truck. And then they have, let's say, 0.4 seconds to apply their own brakes, to really move the brakes to the wheel. So every truck is braking within 0.5 milliseconds. And being in such a truck, this is a pretty strange experience, I can tell you, because normally what we expect as drivers is you're driving behind the car or truck in front of you, you see the red lights of the brakes coming on, and your car is still, of course, at normal speed. And then you're approaching that car and then you're slowing down. Here in this case, you're sitting in the truck, the first one is hitting the brakes, you are hanging in your restraint systems, but the distance is the same. The distance just stays 11 meters. It's anyhow very, very, very close, so it's good that the truck doesn't come closer, but you're moving all at the same distance until you stand. And this is, of course, a fantastic thing. It's great for fuel saving, it is great for getting the trucks closer on the road, and it is, of course, an ease for the truck drivers. One needs to drive, 4 can do whatever they like, and these road trains, this was the message in the video, can do the following. The first truck via car-to-car communication can tell a traffic light, hey, I'm a road train, I'm not one truck, I'm 5 trucks long, so you better give me a green light extension. Don't switch to red now, keep it for 10 seconds until we are all past the crossroads. So we don't have to slow down, we don't have to consume a lot of fuel again while starting again. But we just can keep going, and the traffic flow is much smoother than it would have been otherwise. Yeah. So there we have a lot of technologies in these truck companies, and of course for the truck companies, it is very, very important to also give the driver enough rest time. The labor cost of a truck driver is 1/3 of the truck operation. Therefore, it makes a lot of sense to have, in the countries where you have to pause every 3 or 4 hours with the truck driver, to have this pause for this resting for the driver done while the truck is still driving. So you're just following the driver in platooning mode, and you can rest, and you can take over then when you're going on your own again. So pretty nice economic use case. As said, there was a lot going on in Europe, field trials, truck platooning. There is a lot going on in Asia, so Korea, I have mentioned, but there is also field trials in Japan and activities in China and in Singapore. And we got surprised at the beginning of this year by this gentleman, and this is the US Minister of Transport, because he showed up at the CES fair in our booth, and he said, I want to work with you, I want to make this a law in the US. Where basically in a few years from now, every new car has to have car-to-car communication. Because he had made the calculation how many severe accidents he can avoid. So what have we done? Together with the US Department of Transport, we have joined an award for the smartest city in the US. There have been 50 cities that had handed in an application. One of the cities, which is Columbus, won this award. They get $50 million now for infrastructure, for making their city smarter. And amongst others, this is the car-to-car communication from NXP. What we also have is, this is a tiny little RFID text here. And all of you know these boring normal RFID texts. These RFID tags here have one special effect, and you can see it out there in the demo floor. These RFID tags work over a distance of 20 meters. So they work from here to the end of this room. Contactless, battery free. And what I've done in Hamburg is I've glued such a sticker into the school bag of my little daughter. And just imagine what is happening then. My little daughter and 40 other kids are driving in a school bus to school. The bus opens its gates, 40 little devils run out and go to the next traffic light. And the traffic light sees, via RFID detection out of 10-15 meters distance, oh my God, there is a huge group of kids. I better switch to green for the kids. And via the car-to-car communication, I warn all guys in the cars and in trucks that are approaching the traffic light, hey, slow down. Anyhow, I'm going to go to red, but you better be careful, here is kids at the crossroads. And you can see this use case outside there. Our guys have set up the demo so that you can see how that really works. So all these technology will end up in this smart city trials, and this, of course, for us, a very nice thing. So the good news is we have all of that robust enough. That's, of course, the job of the semiconductor industry, making it high temperature, robust, that you can put it in a shark fin antenna on the roof of the car. And if you have it in there, yeah, then, of course, you have very short ways to the antenna systems. You have smart antennas under the roof of the car. Very, very nice innovation. I've talked about a lot of sensing systems, but what would be all the best sensors if you don't have a brain in your body? So the next point is, of course, you need to have something that is taking all the sensors information and is calculating a driving advice. And with that driving advice, then you can decide where to steer, how to accelerate or decelerate. So this is a sensor fusion unit, as we call it, or in our language, we have nicknamed it Blue Box, because our reference designs are blue 19-inch test racks. This is a combination of two products from NXP. On the one side, we have supercomputing capabilities, so 80,000 DMIPS in the biggest variant, and 80,000 DMIPS and 8-core ARM architecture, which is basically nothing else than a cloud computing device. So we are normally selling these devices into server farms for cloud computing centers or into the very, very big network routers. So each of those devices is equipped with 8-10 gigabit I/O ports and has quite a lot of compute power. And in parallel, we are putting a so-called functional safety microcontroller. So this is basically functional safety watchdog in the system. And this one is supervising that this one doesn't screw up the calculations and doesn't get disturbed and it doesn't do wrong calculations. Yeah? So together we have a system. Here you see why it is called Blue Box. This is the development rack, the initial one. We have a system that has 90,000 DMIPS of compute power. And the good news is it only consumes 40 watt of power consumption. There is other companies out in the market. Of course, they are offering supercomputers. There is a lot of personal computer companies. And then you very quickly end in 200-300 watts per compute unit, water cooled, which is of course from a construction and quality point of view in a car, a nightmare. And then of course what you also do is you want to have redundancy for those calculation systems. So even if you would put two of those systems in a car, you are at 80 watts, which is quite okay. You don't need any specific cooling for that. It's pretty okay for the power consumption. If you have 2 times 300 watts, 600 watts, there it's getting very, very nasty in terms of really power supplying this device. And this has nothing to do anymore with eco-friendly driving. So this will add significantly to your CO2 balance of the car. So that is very important. We have an open software platform on it, and we are using the inbuilt security of the system, so which is basically ARM, trust zone security, and secure elements that are built in. So 4 of the top 5 car makers have these units at the moment under development. They are playing with these units at the moment, and are putting, of course, their operating systems on, and they're putting their algorithms on, and we are also delivering this to universities and to other people who are playing with self-driving toy cars, robots, or real cars. And of course, that is an open invitation, as I said prior, to get the best algorithms running on these silicon solutions. So when we announced it, we had quite some nice press coverage this year, but this is one of the key ingredients, of course, that you need next to the best-in-class sensing, the best-in-class thinking, and the most power-efficient thinking, because, as I said prior, it is not only about level 4 self-driving, but it is also about level 2 and 3 advanced driver assistance systems, where you need for smaller and lower and middle-class cars over the next years also the right technologies in place. What is the best brain and what are the best sensors? Without a good neural network, so neural system in your body, where you can get, of course, the information from your sensors to the brain, and from the brain to your arms and legs of the car, to the actuators. Well, fortunately, NXP has since 20 years almost, the leading portfolio for CAN-LIN and FlexRay bus systems in the cars. And we have released this year also Ethernet switches and physical layers. So you see here, this is the node count, how many nodes are needed in cars. And here you see a wiring harness. So of course the nodes, the in-vehicle networking nodes as we call it, are more and more important with more electronics in the car. A normal wiring harness has a weight of 30 kilos in the meantime. A wiring harness of a premium car, Mercedes S-Class, BMW 7 Series or so, is as heavy as I am in the range of 80 kilos and has of course more than 5 to 6 kilometers of cable. Huge and very complex systems. And for all of those, at each end, you need such an IDN node, you need a connector and a cable that is connected to the control units of the car. So CAN-LIN and FlexRay, I said, they are pretty much standardized, but the data rate was limited to 10 megabits per second in FlexRay. This is of course not enough. So the next idea was of course then by the auto industry, hey, let's take Ethernet. Because Ethernet is available in all PCs, we can steal it from there, we have all the software stacks, we don't need to invent anything that is proprietary for automotive. But 100 megabit Ethernet has one disadvantage: 4 cables. And 4 cables are of course way too heavy. And you have 2 cables for a CAN network, and now you have to double up. That's ugly. So we looked around in the industry and we found that Broadcom had already invented a standard, Broad Reach that was called, for 2-wire 100 megabit Ethernet. We, NXP, licensed that standard from Broadcom and developed our own chips based on that Broadcom patents and Broadcom IP. And what we basically did is we made it automotive robust, so minus 40 to 125 degrees centigrade to have it under all conditions robust. We have diagnostics functions, power saving functions in there. And we have this standardized, so there were Broadcom solutions and NXP solutions. They work with each other, they are robust, and they are released in the market, and they are at the moment in the product ramp-ups at the tier ones and car OEMs. And this is of course changing the setup of these car networks dramatically. The good news of this Ethernet electronics is it can be deterministic. So the last thing that you want in a self-driving robot is that the networks are not deterministic, so that you basically can get wait states. If you are braking and the robot says, or the car says, hey, Lars, wait a second, I'm doing a wait state now, that is exactly not what you want to have. You want to have for certain functions, when you trigger an action, immediate reaction. This is what time-triggered Ethernet is doing. So time-triggered Ethernet is basically doing the following. It is classifying how the data packages are driving in the Ethernet network, and there is certain data packages that get a fast track, that have always priority. And then these non-critical data packages, they have to travel at lower speed, but they are always predictable and fast. And this is of course a fantastic mechanism that we need for all these X-by-wire functions. Brake-by-wire, steer-by-wire, fly-by-wire in airplanes. What is it all going to lead to? Well, I said prior, I know from the German car industry, and this is absolutely not different here in Korea, that the premium cars are going to control unit amounts somewhere between 150 and 250 ECUs for a luxury car. And all the others are following this as more electronics as it is coming in. So if you have cars with 250 control units, it will for sure not be anymore one CAN wire and a few control units linked into that. No, it needs to be much more complex networks. And we are going to more and more domain-based networks, like we had 10 years ago in big office buildings where a lot of computers were installed. Now you have basically 250 rooms in your office building. Every room has a computer, so this is your ECUs. And you have basically big routers, big gateways for the various branches, first floor, second floor, third floor, fourth floor, or in other words, different domains of the car. And you have basically here in those areas, in these different compartments, you have all the time Ethernet connectors or in some of the sub-branches then, for example, flex-ray or CAN connections, where it makes sense. But by and large, you have a tree structure where all the various branches have separated functionality and where they can also security-wise be separated. And of course, for these switching activities, you need the Ethernet PHYs and the Ethernet switches. I mentioned it already. In the past, we had very simple networks, one CAN bus, and everything hooked up to that CAN bus. In the bigger, newer car networks, you have one gateway, and a lot of these sub-branches linked to that gateway. And now you need to make that whole thing secure against hacking. Well, what can we do? Very simple. It's very similar to your house. If you have a house at home, the heaviest security you want to apply is to the interfaces to the outside world. You want to protect your front and your back door as much as possible. So at the front door of your car, here for example the telematics unit, you're bringing in the heaviest security possible. And this is for example in the Telit products out there. So some of the Telit products that you see out there, they are in the Audi Q7, there I know it, and there basically our chips for the passports that we have, they are integrated there to just make sure that no one can hack into such a system from the outside world. So heaviest crypto security is used in that. Then, if you're coming into your building with the 250 rooms and the 250 computers, you have an entrance hall. And in that entrance hall, you have also crypto electronics, or in other words, in your entrance hall, your gateway, you have a few Doberman dogs sitting, and they are watching that no one from the infotainment wing of your building moves to the engine management wing of your building if this is not authorized. Gateway security. So NXP has a lot of gateways in the portfolio, and of course we are having there the right levels of crypto security. And then what you of course are doing is each of the rooms has a microcontroller, has a PC in, so to say, so an ECU, a control unit in, with microcontroller embedded security. So also there again, crypto cells are on these microcontrollers. And the fourth level of security that we are doing is we are checking which traffic is communicated over those network branches. Why? Well, you very simply can find hacks by that. Just imagine you have a trailer hook ECU that is just made for switching the indicators when you have a trailer hooked up to your car. If that trailer hook ECU suddenly sends the command over the CAN bus, hey guys, please all lower your windows and open the doors. Yeah, then at least someone in the network should ask, hey, why are you authorized to send this command? Or in the house example, there would be you are inviting guests for dinner at home, and suddenly they show up in your wine cellar or they show up in your bedroom without you knowing. And then at least you should ask the question, how comes that you are showing up in totally unexpected places? So it's not about crypto security and encryption, it is more about network hygienics and understanding, is this all consistent what I see? And our physical layers for the CAN PHYs, for example, have embedded capabilities in some of the devices. But we just can say, take the existing CAN PHYs, replace them with this type of network checkers, and at least you get a base level of security into the system. And this is what we are calling 4 layers of security. The heavy-duty secure interfaces to the outside world, secure gateways, secure microcontrollers, and this network hygienics. And with that, we have a pretty mighty system in our hands, how you can secure your entire house, to get back to that example, without having everywhere heavy-duty door locks, because between your living room and your kitchen, you do not want to have 3 or 4 door locks that you, every time you're moving from one room into the other, have to unlock and have to lock again while you're moving the rooms. That is not convenient, you would not want to have this at home, and of course it would be also totally overdone in a car to having at every interface this heavy-duty security. But finding the right level of security is such a functional security system task that I have described right. So I haven't said all in all, we are of course trying to leverage our crypto chip experience, the vast majority of these patents of NXP, and you see it here. It's quite a mighty ecosystem that I, fairly spoken, try to steal from my sister business units and try just to lift over into automotive. So there is not a lot of new standards that we need to identify, need to define. We just need to take what we have in the banking part, in the passport segment, in the health, in the e-government segment, and bring it into automotive and make sure that the car is as secure as every other IoT device that you can think of. So coming to an end, what does that mean is, of course, what I'm doing here is a bit of storytelling to inspire you to get the right use cases in correlation with what is possible with silicon in cars in a few years from now. And this is just a cross-section of the activities that we have driven over the last year. So this is the trucks that are negotiating with the traffic light and with the kids and the school bags. Here you see what we have done on a racetrack. This is basically an autonomous driving car from Volkswagen, so driverless car. The car was just going rounds, no one touching it, no one in. And then you see these ladies here with this green bag, and they were walking with these RFID tags in the back. The traffic light here sees the tag, and then it's via car-to-car communication, informing the self-driving car already 500 meters in advance and say, hey, slow down. You have to stop at this traffic light. You stop here until you get the okay from the traffic light again that every pedestrian is gone. And how do you detect that the pedestrians are gone? Well, no RFID tag inside anymore, and with our tiny little radar systems, you can detect a big bag of water very accurately. And I'm nothing else than an 80 kilo big bag of water with a few bones in it. So the signal of a human body you can very, very nicely get, so you can spot whether the walkway is free again or not. This guy is Andy Greenberg. This is the guy who hacked the Jeep last year, and we had been there in a security discussion at Frankfurt Motor Show. And what happened last year to me in the Bay Area, in California, was some of the guys said, if you can do car-to-car communication, can you also do drone-to-drone communication? It works over 1 kilometer, 1.5 kilometers, and it works up to relative speeds of 500 kilometers per hour. So why can't you build anti-collision transponders? I said, okay, what exactly do you mean? What do you need? He said, for delivering an Amazon parcel, 3 kilos of a parcel over 20 kilometers. You need to have a little drone, and this drone is delivering that parcel. But if you're flying outside of the line of sight, we have to have anti-collision transponders. And the Lufthansa anti-collision transponders have 10 kilos of weight and are that big. If you want to deliver a 3 kilo parcel, have a 10 kilo anti-collision transponder, that doesn't make any sense. So can't we get your 14-gram modules that work over 1 to 2 kilometers, and can we use them as anti-collision transponders from drone to drone? And by the way, these systems, of course, have a crypto chip, a little passport chip inside. Because an ambulance has to go to a traffic light and has to say, I'm an ambulance, switch me to green. If there would not be a passport chip inside, my car, my passenger car, would go to every traffic light in Hamburg and would say, hey, I'm an ambulance, switch me to green. Then I'm 10 minutes faster in the office than you. Yeah? So I would cheat the system, and that of course would not work. So we have this authentication. The drones can even tell the police cars, I am a legal drone, I'm allowed to fly here. And this again is important for the Winter Olympics in 2 years from now. Because the only thing that you don't want to have is, you do not want to have any terrorist flying a drone with 3 kilos of explosives into an Olympic stadium. But what you still want to have is, you want to have, of course, the TV drones in the air to take movies of the athletes. And then I was talking to the Ministers of Transport and the London Minister of, UK Minister of Transport. He said, yeah, Lars, you are right, we had this for the London Olympic Games already. In those days, we were thinking of some idiots, Al-Qaeda idiots with a Cessna plane, so a much bigger flying object, flying explosives into the stadium. And we had anti-aircraft guns on every building in the city. The problem is just getting more complicated because everyone can buy a drone today. Yeah? So this is getting very dramatic. Those you have heard, the truck platooning you have heard. And the last thing that is exciting me is basically this little student motorbike here. Little means it's a 450 kilogram electric motorcycle that is at the moment used to drive around the world by these students. And here I have a ring at my finger. And this is a ring that I got from my boss. As funny as it sounds, I didn't get it from my wife. This ring here is containing an NFC chip and again one of our passport chips. And with this ring, I can start or stop the motorcycle. If I touch the bike handle, I can drive. If any one of you touches the bike handle, nothing happens. So this is again high-end electronics, and this is basically what we are playing with. So in a box, we have loads of these Lego systems. We have loads of the system solutions. We would like to invite you to play with all of that, with the fusion parts, with the sensing parts, with the security parts, and all of that in conjunction, of course, are the ingredients for robotics and complex IoT devices. And with all of that, I'm coming to an end. So big thanks for listening in, and looking forward to our panel discussion in a few minutes, and the open question, of course, later. Thank you.